Hi, and welcome to the next video in the series of doing a tutorial for creating your first DirectX application in C++, completely from scratch. In our last episode, we defined the viewport and the sysrect and created a 2D triangle rendered to our screen by specifying 3 vertices here that we stored on the GPU in terms of the upload heap, and we did a basic draw call. Since I've been advertising that we should do 3D drawing as the end goal of this tutorial series, I've laid an outline for the next potentially 4 videos, depending on how long we take, where we will do the stepping stones in terms of what is needed to be done to do 3D drawing. Right now, we have a pipeline where our shader programs process our vertices and they translate them directly into clip space / screen space, which means where they should be placed on the actual screen. And as you can see here, our vertices are defined in 2D space since they only have an X and a Y component. This means that this is not 3D. Even if we added a C component, it wouldn't really matter, because whenever the vertex shader here outputs a SV position, it is interpreted as in clip space, meaning screen space. So we might specify a 3D position, but the vertex shader can't really handle a 3D position. It doesn't know what to do with it. And it needs to pass along a 2D position to the rasterization unit and pixel shader. So that's a problem. We need some way of defining a translation method between 3D and 2D space. Also, when you work in 3D, you need to define not only your 3D a translation method between 3D and 2D, you also need to define the actual space. It has to have 3 axes, since it has 3 dimensions, obviously. And you need to define which axis is up, which is forward, which is right. And there are different ways of defining such a coordinate system. And we will look into what DirectX usually does. So let's look up DirectX coordinate system. And let's see, we have an article here. DirectX uses a left-handed coordinate system. And if you're using a right-handed coordinate system, which might be if you're porting from OpenGL, they say that you need to flip the order of the triangle, and you also need to change a so-called view matrix. My own project, which I do here on the channel during live streams, actually uses a right-hand coordinate system, even though if we work in DirectX. But that's because I usually do Blender for modeling, and that uses OpenGL, and therefore we need to use a right-handed sided coordinate system. Otherwise, I had to do a lot of computations to the models and so forth, and I haven't done that yet. So, but in this series, we will be using the intended left-hand coordinate system. There are some functions here referenced that if you want to obtain a translation method for a right-handed coordinate system, DirectX Math provides utility functions for that. All right, but what am I actually talking about in terms of translation? Imagine that this box here contains a 3D coordinate system. As you can see inside the box, it has an up axis, it has a forward going axis, and a right going axis. It's defined entirely on all three axes. The box contains 3 components for each vertex, but we need to translate it into screen space so that we can see something rendered to our 2D screen. So you usually do that by defining a eye, a camera, call it whatever you want, but simply a viewpoint. And you define that viewpoint in 3D space in terms of how close to the lens of this viewpoint can you actually go, and how far out can you see. And that is actually a definition of a 3D space. So you need to warp it so you get a proper sense of depth, as you can see here. If you're trying to get a 2D perspective, which is the plane right here, for example, on a 3D object, you need to kind of like warp it so that it gets appropriately smaller or larger the further you are away from or closer to the camera. So you need some kind of translation into a so-called viewing frustum that then again needs to clip, or rather interpret how objects are visible in that scene. So let's see, maybe we can find another model. View projection, matrix, camera, frustum. Let's see. Yeah, I'm not sure I'm properly explaining it, but I hope it makes some sense. So we basically try to emulate this. We will have a 3D object, a near plane and a far plane on the camera, and we kind of need to translate this into some pixels that are mapped onto this plane here. So basically you're casting rays and deciding, well, there's an object here, but the rays that I've cast tells me that this object is blocking, so I won't be rendering that. But out here I can look besides this object and see something in the distance here, so I need to render that on my 2D plane. Let's see. Yeah, so it's basically a way of using clipping planes, a frustum, and 3D matrix computations to translate something from 3D coordinates into 2D screen space. Yeah, that is called the view and projection matrix, and usually you multiply those two matrices together so that you have a combined matrix that handles translations directly mathematically from 3D space with 3 coordinates into 2D space with only 2 coordinates. We will use DirectX Math to set up our matrices. Let me see, did I include it in here? Minimum, let's see, in the PCH, we did include DirectX Math. So DirectX Math has some different ways of defining different structures. Let's see. Yeah, we have different types, but we also have vectorized structures for intrinsics. We can store something called an XM matrix, which is basically an intrinsic version of a structure that holds 4 registers with 4 input points. Yeah, since we are doing matrix by matrix multiplication, we will do that. Let's just explore what the DirectX math library has to offer us in terms of coordinate systems. So let's just start defining a view matrix. A view matrix is a definition of how do we define the axis of our world. Which direction is right, which direction is up, which direction is forward, and do we have any specific offsetting or yeah, something like that. It's called translation in terms of math. So let's see, can we actually ask DirectX to get us a view matrix? Well, matrix. Okay, it probably start with matrix here. View. No. Orthographic perspective. Perspective might be the one that we're looking for. Let's look further down here. Okay, we will do a quick search. View matrix. Builds a view matrix for a left-handed coordinate system using a camera position and an up direction and a focal point. So if we define a position for a camera in 3D coordinates, a upgoing vector and a or rather a forward-going vector, something that or rather, let me rephrase that. If we define a focus point, that could be our origin, and a up direction, DirectX can DirectX Math can computate how our view matrix, which is the way that the camera coordinate system is set up, should be created. So I forgot to say that it's not actually the coordinate system of the world, but it's the coordinate system of the camera, because each vertex has to be transformed into the camera coordinate system so that we can do frustum calculations on the actual objects. It doesn't, if they are in 2 different coordinate systems, one is in world coordinate system, the coordinate system of the world, and one is in the coordinate system of the camera, these positions won't match, and you would get weird clippings in terms of when you try to use the so-called projection matrix to translate those vertices into 2D clip space. So you define the camera coordinate system, and you use that matrix to translate from world coordinate system into a camera coordinate system, and then you use those camera coordinate system coordinates, which are still 3D, to use a projection matrix to translate that into 2D. Hopefully that made sense. Anyway, we will use a matrix here. Let's see. Didn't we have a method or a data structure for that? Let's see. XM matrix. Okay. And let's call this our view matrix. We will set our view matrix to, yeah, let's just try using this method. We can use other methods, but this one is probably fine. I've used it before. And we need to look at left-handed. There we go. So we need to specify a vector in terms of where is our camera. Since we are using a left-handed coordinate system, we see that y is up, c is forward, positive c is forward, positive x is right. So let's say that our camera here is completely dead center on the x-axis, but it's maybe 1 unit up on the y-axis, and then it's 3 units translated backwards on the what do you call it, c-axis. And then since this is a XM vector, which is actually a register that contains 4 values, you need to specify the last component as a 0. Yeah, DirectX Math uses these vectors that are intrinsic related, which basically is a 128-bit register with a space for 4 floating point numbers. So it's actually like an array of 4 floating point numbers, even though we only use the first 3. So that's related to the type. Then we need to set the focus position, and we simply set that to our origin in world space coordinates. Remember, this is all in world space coordinates, and the method will do the computations in terms of figuring out how the camera coordinate system is supposed to be set up. So let's define our up direction in world space coordinates. So we remember that y is up. So we define a so-called unit vector, which has the length / magnitude of 1 as the up direction. And since it's an intrinsic, rather a register, we need to specify the 4th component, even though we don't care. All right. So now we actually have a view projection matrix, or rather view matrix. We also need the frustum matrix, which is actually a matrix here that builds a left-handed perspective projection matrix based on field of view. Let's just do that because we like field of view, and it's of course left-handed. We will do a DirectX XM matrix projection matrix, and we will set that up as a thing here by XM matrix perspective field of view, and we need to specify a angle for our field of view. And I think this is in radians. Let's see. Yeah. So how, let's just do a quick calculator for people who um, uh, um, are used to working in degrees. Uh, Online calculator. Enter degrees. Okay, we want a field of view of maybe 70 degrees. Okay, so that means we have a radian value of this. And then we want an aspect ratio. And let's do 16 divided by 9, a classic aspect ratio. We want to define our near plane in terms of distance and maybe a max viewing distance of 50. Why, thank you. And this is basically what we need to do in terms of creating a projection matrix. So let's review what we just created. We created a matrix that translates from world space coordinates into the camera's coordinate space. So that means that every vertex defined in a world space coordinate system can be multiplied by the view matrix to be translated into the camera's coordinate space. Then we have defined a projection matrix that takes anything in the camera coordinate space system and translates that into a 2D mapped position. In math, you can do several operations with matrices at once. You just need to multiply the matrices. So we will store on our rendering API a matrix that, let's see, yeah, I probably need to include the math library here. DirectX math. There we go. Where we call it View Projection Matrix. Yeah, it's a long name, I know, but I just want to be clear about what we're actually doing. And we will store that as our view matrix times our projection matrix. And this will do both translations to any vector slash vertex with 3D coordinates in world space coordinates into 2D space. So let's just use the debugger here to see what we actually end up with. In terms of math here, we do some computations, we do this. Let's see. Now we should have our view projection matrix, and sorry if you can't see it on the video. Maybe I could increase the size a bit here. Yeah, let me do that. Fonts and colors. Let's see the autos and increase the, okay. No, I have to redo it. Anyway, this matrix here contains some components. On the x-axis, it's supposed to do translations like that. Then on the y-axis, it's supposed to do like that, and yeah, so forth. So this basically contains our information. It contains some numbers. I can witness that, even though you might not be able to see it on the stream or the video. We could maybe just redo it. Let's see, just for good measure. Nah, well, okay, it didn't register. Anyway, so that is basically it. In terms of what we wanted to do for this video, we created a coordinate system. We created a translation between coordinate systems, since we have not only one coordinate system, but two. We have the world space coordinate system that is defined like this, with an origin at 0, 0. Then we have defined a camera that has its own coordinate system, and we have created a frustum that can be used to extrapolate vertices in camera space into 2D. So that's it. Hopefully my explanations weren't that confusing. If so, I'm sorry, but that's it for this part of the video. We didn't do a lot of coding here because, yeah, well, we needed to get the math sorted, otherwise it wouldn't make any sense what we were doing in the future. In the next episode, I'll show you how to actually upload this information to our GPU pipeline. And in the video after that, we will do the actual 3D rendering. All right. Thanks for tuning in. Feel free to comment, like, or subscribe if you found any of this helpful. Hopefully, I'll be seeing you in the next one. Bye-bye.